Welcome to Energy Talks, a regular podcast series featuring expert discussions on power system testing, data management, cybersecurity, and important trends in the power industry. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. In this episode, we are diving into the heart of power generation at utilities and industrial plants, where the reliable operation of motors and generators plays a critical role. More specifically, we are going to discuss the basics of rotating machine testing to help keep these machines running reliably. Joining me is Alexander Herrera, an OMICRON applications engineer who specializes in rotating machine testing. Alexander has spent a lot of time recently in front of the camera for a new OMICRON video series about the basics of rotating machine testing, where he demonstrates step-by-step how to perform recommended diagnostic tests and also how to interpret the data to reliably detect developing defects and prioritize condition-based maintenance to prevent machine failure. In addition, Alex will explain why following safety protocols during testing is essential. He will also highlight the importance of comparative measurements and offer useful tips for testing rotating machines. So without further delay, hello, Alex. Welcome to Energy Talks.
Thank you, Scott. It's a pleasure to be here.
Alex, many of the machines powering our infrastructure are now approaching the end of their lifespans. What are the specific risks of navigating reliability while budgets and technical teams are shrinking?
Well, the main risk is that we are asking many machines to operate beyond their originally expected service life, but with less margin, less time for maintenance, and often fewer experienced people available to assess their condition. For large motors and generators, aging does not usually happen overnight. The insulation system, the stator core, the rotor, the end windings, and the mechanical support structures are all exposed to thermal stress, electrical stress, vibration, load cycling, contamination, and moisture. Over many years, these stresses accumulate. The challenge is that many of these degradation processes are not visible during normal operation. Machine can appear healthy from the outside, but internally the insulation may already be weakening. When budgets and technical resources are limited, the biggest danger is making maintenance decisions with incomplete information. That can lead to two problems. Either we overhaul machines unnecessarily, which is expensive, or we miss early warning signs and suffer an unexpected failure. That's why condition-based diagnostics are so important. They help us focus the available budget and expertise on the machines that truly need attention.
Interesting. Electrical insulation is an important component to look at in terms of machine reliability. Why is the stator winding considered the most valuable component, and why is specialized electrical testing needed to give operators more visibility into the condition of their machines?
Stator winding is one of the most vulnerable components because it is exposed to several stresses at the same time. Electrically, it has to withstand the operating voltage and transient overvoltages. Thermally, it heats up and cools down depending on the load. Mechanically, it is exposed to electromagnetic forces and vibration. Environmentally, it might be affected by humidity, dust, oil, chemicals, or other contamination. All these factors act on the insulation system. Over time, they can produce cracks, delamination, voids, surface striking, looseness, or partial discharge activity. The difficulty is that insulation degradation is often hidden. You cannot fully evaluate the health of a stator winding only by looking at it from the outside or by monitoring temperature and vibration. Specialized electrical testing gives us a deeper view. Tests such as insulation resistance, polarization index, capacitance, tan delta, width and voltage and partial discharge measurements each look at the insulation but from a different angle. Together, they help us understand whether the winding is clean, dry, mechanically stable, electrically strong, and free from active local defects.
In your new YouTube video series, you start with measuring insulation resistance and polarization index. Why is this considered the first line of defense for deciding if a machine is even safe to energize it for further testing?
Well, insulation resistance and polarization index are normally the first line of defense because they help us detect major insulation problems before applying more demanding test voltages. The insulation resistance test gives us an indication of how well the insulation is resisting DC leakage current. If the measured resistance is very low, it may suggest moisture, contamination, surface leakage, or serious insulation deterioration. The polarization index adds a time component. It shows whether the insulation resistance improves during the test, which is typical for a healthy and dry insulation system, or whether it remains low and unstable, which can be a warning sign. I like to describe insulation resistance and polarization index as a basic safety and condition screening. They do not tell the complete story of the insulation, but they help answer a very important first question. Is this machine in a reasonable condition to continue with further diagnostic testing? If the answer is no, then applying higher voltages without further investigation could be risky.
Alex, the next measurements you performed in part 2 of your video series about the basics of rotating machine testing are the capacitance and tan delta measurements. In these measurements, you compare resistive and capacitive currents. How do these measurements help a testing engineer assign a health grade to a machine's insulation system?
In a healthy insulation system, the current is mainly capacitive. That means the insulation behaves mostly like a dielectric between the conductor and ground. But real insulation is never perfect. There is always a small resistive component, which represents the electric losses. Tan delta, or dissipation factor, or power factor, measures the relationship between these losses and the capacitive current. When tan delta is low and stable, it usually indicates that the bulk insulation is in good condition. When tan delta is high, or when it increases significantly with voltage, it can indicate aging, moisture, contamination, delamination, voids, or other insulation defects. That's why this test is useful for assigning a health grade to the insulation. It gives us a global view of the electric condition of the winding. Capacitance is also valuable. Changes in capacitance can indicate changes in the insulation geometry, moisture absorption, or delamination. So together, capacitance and tan delta provide a very important picture of the overall condition of the main insulation system.
The next measurement you performed in part 3 of the video series is the voltage withstand measurement, also known as the overvoltage or high-pot test. This is a more aggressive assessment. Why do you specifically recommend performing this measurement with AC voltage to verify that the insulation can handle its rated voltage within a safe margin?
The AC withstand test is not a test I will use casually or repeatedly without a clear reason. It is more aggressive than diagnostic trend measurements, but when applied correctly, according to standards, OEM recommendations, and the condition of the machine, it gives very valuable confirmation that the insulation still has enough dielectric strength and safety margin for operation.
So another test you perform in part 4 of your video series is often referred to as the ultimate predictive tool. This is the partial discharge, also known as PD measurement. What can a PD measurement see regarding microscopic voids or resin bubbles in stator winding insulation that the other 3 tests might miss?
Well, partial discharge testing is powerful because it can detect local defects inside the insulation system before they become major failures. A small void, crack, delamination, or resin bubble inside the insulation can create a local concentration of electric field. When the electric field in that small cavity becomes high enough, a tiny electrical discharge occurs. That is what we call partial discharge. The important point is that This defect may be very small and very local, and because of that, it may not significantly affect global measurements, such as insulation resistance or tan delta in the early stages. PD measurement can detect this electrical activity. It does not simply give us one number. It can also provide information about the discharge pattern, the severity, and sometimes the possible defect type or even location. For me, PD is one of the most valuable predictive tools because it helps identify active insulation deterioration while there is still time to plan maintenance instead of reacting to a failure.
Alex, before touching a machine to perform electrical testing, it is vital to follow a specific safety protocol. Could you please walk us through the 5 safety rules for electrical testing and tell us why earthing and short-circuiting are so critical when performing diagnostic measurements on machines?
Absolutely. Safety must always come before testing. The 5 safety rules are: first, disconnect completely. Second, secure against reconnection. Third, verify the absence of operating voltage. Fourth, carry out earthing and short-circuiting. And fifth, provide protection against adjacent live parts. The fourth rule is especially important during diagnostic measurements because large machine windings behave like capacitors. They can store electrical energy during testing, especially after DC tests, such as insulation resistance or polarization index measurements. There can also be induced voltage from nearby energized equipment, connected cables, or electromagnetic coupling in the substation or plant environment. By earthing and short-circuiting, we make sure that the winding is discharged and held at earth potential. This protects the people working on the machine and prevents dangerous voltage reappearance. In high-voltage testing, grounding is not just a formality. It is one of the most important barriers between a controlled test and a dangerous situation.
Alex, can you describe the importance of benchmarking test results and why you consider a single test result just a data point, but a trend, a diagnosis? If you do not have the original factory acceptance or FAT test data, how do you begin to establish a reliable baseline for benchmarking?
Factory acceptance test data is always valuable because it gives us the original fingerprint of the machine. But in practice, especially with older machines, data is often missing. In that case, the best approach is to create a reliable baseline starting from the next well-performed diagnostic campaign. That means the test setup must be well documented. The engineer should record the test voltage, temperature, humidity, connection method, grounding configuration, instrument used, and the condition of the machine at the time of test. From there, future measurements should be performed as consistently as possible. The absolute value is important, but the trend is often even more important. We can also compare the results with similar machines, previous service experience, industry guidelines, and OEM recommendations. The key message is this: if you do not have a historical baseline, start building one now. A single result gives information, but repeated and comparable results give insight.
Now, we have covered the 4 measurements on stator windings. These again are insulation resistance and polarization index, capacitance and tan delta, voltage withstand, and partial discharge. In addition to these, there are a few additional recommended tests one can perform on a machine's stator core and rotor. Why should one also keep an eye on the condition of these machine components?
Because a rotating machine is not only a stator winding, it is a complete electromagnetic and mechanical system. The stator core is responsible for guiding the magnetic flux. If the insulation between core laminations is damaged, circulating currents can develop. These currents can produce local overheating and, in severe cases, major core damage. The rotor is also critical. Rotor winding problems, turn-to-turn shorts, mechanical looseness, thermal imbalance, or deformation can affect the magnetic field, increase vibration, reduce efficiency. So even if the stator winding tests look acceptable, the machine may still have serious problems in the core or rotor. A complete condition assessment should include all critical components. That is the only way to understand the real risk of the machine as an asset.
One of these tests you show in part 5 of your video series is the stator core low energy, or LCID test. What are the warning signs you can detect with this test that the interlaminar insulation is failing, and how does this test prevent a damaging core melt?
The stator core is built from many thin steel laminations. Each lamination is insulated from the next one. This interlaminar insulation is essential because it limits eddy currents. If that insulation is damaged, local circulating currents can appear between laminations. These currents produce localized heating. The warning signs are areas with abnormal magnetic losses, localized heating, or increased fault current detected during the test. This damage can come from mechanical impact, foreign objects, overheating, previous repairs, or vibration. The so-called LCID test helps us detect these problem areas at a relatively low excitation level. That is a major advantage because we can identify core faults without needing to fully excite the core to the rated flux. If these defects are not detected, local heating can grow and eventually cause severe core damage, sometimes referred to as a core melt. That type of failure can be extremely expensive and may require major core repair or replacement. So LCID is a very useful preventive test. It helps us find localized core defects before they become catastrophic.
For the sweep frequency response analysis, or SFRA, on rotors, you inject a signal from hertz to megahertz. How does this wide frequency range help you catch a tiny short circuit between winding churns?
SFRA works by creating an electrical fingerprint of the rotor winding over a wide frequency range. Different frequency ranges are sensitive to different physical and electrical characteristics. At lower frequencies, the response is influenced mainly by inductance and magnetic behavior. At higher frequencies, capacitance, winding geometry, and local connections become more influential. If there is a small turn-to-turn short circuit, the electrical path in the winding changes. That changes the inductance, losses, and sometimes the capacitance of the winding. These changes appear as deviations in the frequency response. The value of SFRA is that it is very sensitive to small changes. By comparing the response with a previous measurement with another pole or with similar rotor can identify abnormalities that may not yet be obvious during operation. So SFRA helps us detect developing rotor winding problems before they evolve into more serious electrical or mechanical failures.
So cross-test correlation seems to be an important area to cover. For example, if an engineer sees low insulation resistance or polarization index, but high tan delta levels, for example, how does cross-testing help us decide if the machine simply needs cleaning or drying or even a more thorough intervention?
Cross-testing is essential because each test sees the insulation from a different perspective. Low insulation resistance or low polarization index often point toward moisture, contamination, or surface leakage. High tan delta can also be caused by moisture or contamination, but it may also indicate deeper aging or degradation of the bulk insulation. So, if both insulation resistance, polarization index, and tan delta are poor, the first question is this a surface or environmental problem, or is it an internal insulation problem? A practical approach is to inspect, clean, and dry the machine if moisture or contamination is suspected, and then repeat the measurements. If the results improve significantly, the problem was likely related to surface condition or humidity. But if tan delta remains high, if it increases strongly with voltage, if capacitance has changed or if partial discharge activity is present, then we may be dealing with a more serious insulation degradation mechanism. That is the value of cross-testing. It reduces uncertainty and helps avoid both overreaction and underestimation.
How can an asset manager use this condition-based data to prioritize a targeted diagnostic outage instead of a costly general overhaul of a machine?
Condition-based data allows the asset manager to move from calendar-based maintenance to risk-based maintenance. Instead of saying, this machine is old, so we need to overhaul it, we can ask a better question. What is the actual condition of this machine? And what is the risk of continued operation? If diagnostic tests show stable results over time, the machine may not need a major intervention immediately. But if the data shows increasing partial discharge activity, rising tan delta, low insulation resistance, abnormal core indications, or widening deviations, then that machine should receive priority. This allows the asset manager to plan a targeted outage. The outage can focus on the specific component and failure mechanism indicated by the diagnostic results. That means less downtime, better use of maintenance budgets, and a lower risk of unexpected failure. In other words, condition-based data helps convert technical measurements into practical maintenance priorities.
What is one common mistake or misunderstanding you see most often during offline testing that should be altered or avoided?
One common mistake is comparing test results that are not really comparable. For example, an engineer may compare today's insulation resistance or tan delta result with a previous value, but the temperature, humidity, test voltage, grounding configuration, or connection method may have been different. In that case, the difference in the result may not come from the machine. It may come from the test conditions. Good diagnostics require consistency. The setup must be correct. The machine must be properly isolated. The grounding must be well controlled. And the environmental conditions must be documented. The other important point is interpretation. A test result is not just a number. It must be connected to the physical condition of the machine. So my advice is do not only measure correctly, document carefully, and interpret results in context.
So Alex, before we go, do you have any last tips or words of advice to our listeners about the basics of rotating machine testing?
Yes, I do. So my main advice is to be proactive and systematic. Rotating machine failures often give warning signs before they become catastrophic. The challenge is that we need the right diagnostic tools and the right interpretation to recognize those signs early. Start with safety, then use consistent test procedures, build trends over time. Do not rely on only one test. Combine the results and look for the story behind the data. Also, remember that diagnostics do not replace engineering judgment. They support it. The real value comes when we connect the measurements with machine design, operating history, maintenance history, and failure mechanisms. When we do that properly, testing becomes much more than a maintenance activity. It becomes a powerful tool to improve reliability, reduce risk, and extend the life of critical assets.
Very well said. Alex, thank you for joining me for this episode of Energy Talks.
Thank you, Scott. It was a pleasure to join you and talk about this important topic. I hope this discussion helps listeners better understand how rotating machine testing supports safe, reliable, and cost-effective operation of critical electrical assets.
Very good. Well, thanks again, Alex. And a big thank you to our audience for listening to this and other episodes of Energy Talks. We always welcome your questions and feedback. Please send us an email to podcast@omicronenergy.com. OMICRON has several years of experience in power system testing, data management, and cybersecurity, and offers a matching solution for your application. For more information, visit our website at omicronenergy.com. Please join us for the next episode of Energy Talks. Goodbye for now, everyone.